So I want to talk about basically an old question, which is about convexity in symplectic geometry. So in this talk, we're going to stay in R2N with standard symplectic form. So we are in R2N with omega 0, which is the sum of dxi wedge dyi. And we're interested in convexity because convex domain have, I would say, conjecturally very strong rigidity properties. So convex domains have very strong, or I would say conjecturally very strong rigidity properties. But convexity is not a symplectic notion. What I mean by that is it is not invariant on the symplectomorphism. So to convince ourselves of that is if you look in R2, a symplectomorphism is a diffeomorphism which preserves the area. And so it's very easy to break the convexity in R2. You can send anything convex on anything same area, but not convex. So the question, which actually is a pretty old question, is what is the right symplectic notion for convexity? So what is the, I want to say, right notion of convexity? The right symplectic notion. Of course, when I say what is the right or the correct symplectic notion, it might strongly depend on what you're interested in. So I want to start by making a digression about what is my interest in convexity, and then explain various ideas on what to replace convexity by symplectic notions. So my interest comes from symplectic topology and symplectic embeddings. So this basically started with Gromov non-squeezing theorem, where he proved that the ball of size R symplectically embeds in the cylinder of size R. So that's the disk times R2n minus 2. If and only if the size of the ball is less or equal than the size of the cylinder. So, I mean, a very general problem in symplectic topology is to classify symplectic embeddings, but even more basic than that, it's given two symplectic manifold, does there exist a symplectic embedding from one to the other? And one of the core tools to study symplectic embeddings are symplectic capacities. So what is a symplectic capacity? So it is a function, so a symplectic capacity is a function which assigns a number to each symplectic manifold, or in a restricted class, so which assigns to each symplectic manifold x omega a number. So, it's a function, let me call it C, which is a number C of x omega, which is a positive real number or plus infinity, such that first it is monotone. So if I have two symplectic manifold x and y, and if x embeds in x prime, then the number associated to x is less or equal than the number associated to x prime, oh, if x embeds in x prime, then C of x omega is less or equal than C of x prime, omega prime. And it behaves well when we scale the symplectic form. So if we take a positive real number, then C of x and R times omega is R times C of x omega. Of course, the function which associates 0 to every symplectic manifold or plus infinity are symplectic capacities, maybe not the most interesting if you really want to obstruct symplectic embeddings. So there's a normalization condition, and I would say that the capacity C is, and let me call it ball normalized. If on the ball of size 1, it is equal to 1, and it is also equal to 1 on the cylinder of size 1. So it's an extremely strong normalization condition because it's kind of a double normalization condition. And we have note also that the existence of a ball normalized symplectic capacity is equivalent to Gromov's non-squeezing theorem. So we have examples of ball normalized symplectic capacities. Well, first there's the Gromov width, which was introduced by Gromov after his theorem. Of course, he didn't call it that way himself. But... So the Gromov width of x omega, this is the size of the largest ball one can symplectically embed in X. So it's a supremum of R such that there exists a symplectic embedding from the ball to R, to X. Then similarly, there's the cylindrical capacity. So CZ of x omega, this is the smallest cylinder in which one can embed X. So this is the infimum over R such that there exists an embedding from X to the cylinder. Then there have been other examples. So Ekland and Hofer introduced a sequence of capacity, the first of which is ball normalized. Hofer and Zehnder introduced a capacity, then Viterbo introduced a capacity. Myself with Hutchings, we introduced a sequence of capacity, the first of which is normalized, and there's many more. We have many examples from many different definitions. But then there's about capacities, there's a conjecture by Viterbo. That for convex set, we have an isoperimetric inequality. So if X in R2N with standard symplectic form is a convex set, then for any ball normalized symplectic capacity, one has that C of X to the power n is less or equal than n factorial times the volume of X. with equality if and only if X is symplectomorphic to a ball. Note that when here I wrote volume of X, I mean here the Euclidean volume. And so n factorial times the volume is the symplectic volume. That's like n factorial times the volume is the integral of omega 0 to the n over X. Okay. So, well, we have examples of ball normalized symplectic capacity, so we can try the conjecture on the capacities we have. And so first lemma is if we try with the Gromov width, then yes, the conjecture is true. So if X in R2n is convex, then yes, the Gromov width of X to the power n is less or equal than n factorial times the volume of X. Then we have all those other symplectic capacities here, which I haven't defined. I'm just saying they exist and with various definitions, but that's. And let me start by quoting a theorem, and I should cite many people here. Certainly Eklund and Hofer and Zender, Abodandolo and Kang, Irie, and I'm sorry for all the people I'm forgetting, is that if X is a convex set, is convex, then all those capacities are actually equal. So the Eklund-Hofer capacity of X is equal to the Hofer-Zender capacity of X, is equal to the Viterbo capacity of X, is equal to this capacity defined using positive S1 equivalent symplectic homology of X. And all of those are equal to the smallest period of a periodic Reb orbit on the boundary of X. So they are given in terms of dynamics on the boundary of the convex domain, and like shortest orbit they're on. Yeah? Then you say, okay, we know what they are on convex sets. Is the Viterbo conjecture true? So do we have that if X is a convex set in R2n, do we have that this smallest period, which I call the systole of X to the power n, is it less or equal than n factorial times the volume of X? Completely unknown, not even in dimension 4. This is called the weak Viterbo conjecture. And Claude pointed to me many times that when I mention weak Viterbo conjecture, the weak refers to conjecture and nothing. But then one might wonder, is it an accident that all these capacities are equal on convex sets? And the answer is no, and that is called the strong Viterbo conjecture. Which I've been quite obsessed with those last few years, is that on convex set, all ball normalized capacity coincide. So all ball normalized symplectic capacities coincide on convex sets. Yeah, so that is actually my main interest in convexity, and that's where I come from. So now that this is quite clear, let's go back to symplectic convexity and what would be a good symplectic analog of convexity having this strong Viterbo conjecture in mind. So maybe the first idea is to say, well, convexity is, or let's call it symplectically convex, is being symplectomorphic to a convex set. Morphic to a convex set. Sure, that would solve the problem. But now, given a non-convex domain in R2N, is it symplectically convex or not? I don't know any criterion to determine it. That would require to know the entire symplectomorphism group, which is completely out of reach. So we would like a more geometrical description of that. Then I would say second idea, due to Hofer, Wysocki, and Zehnder in '98, is let's replace convex by dynamical convexity. So dynamical convexity, let me not define it properly, but it's just something on all the orbits on the boundary, namely that all periodic Reb orbit on the boundary have Cournot-Zehnder index at least n+1 or something. The great thing is it's invariant under symplectomorphism, and they proved that every convex set is dynamically convex. So convex implies dynamically convex. So that's great. And if you're interested in dynamics, most results that you want for convex set, like dynamical results you want for convex set, are true for dynamical convex set. But the 4 years ago, 3 years ago, I should have checked. 4 years ago, there was a theorem by Abondandolo, Bramham, Chiniewicz, and Salomao, is that for all positive epsilon, they build a dynamically convex set, convex domain. Let me call it C epsilon in R4, such that the weak Viterbo conjecture is wrong on this domain. So the systole of C epsilon squared is larger than 2 minus epsilon times 2 factorial times the volume of C epsilon. And Viterbo conjecture is that it is less or equal than just 2 factorial. So for a while, it was thought that dynamical convexity was equivalent of being symplectomorphic to convex, but then after this theorem, it was either dynamical convex is equivalent to being symplectomorphic to convex, but then Viterbo conjecture is wrong, or Viterbo conjecture is true, but then dynamical convexity is more general than being convex. And well, then 2 years ago, there's been a bit of hope in my direction, because I'm betting on Viterbo conjecture, and it's a result by Julian Childers and Oliver Etmer. Let me decompose it into 2 parts. So first, they found a criterion for being symplectomorphic to a convex domain. So they say there exist 2 universal constants, let me denote it C and capital C, positive, such that all convex sets in R4, okay, in R4 satisfy that if we look at the smallest period of a periodic Reb orbit on the boundary of the convex set, we multiply it by its real invariant and divide by the volume, then it's bounded below by a small constant and bounded above by this big constant, which are the same for all convex sets. So this real invariant, I think it was defined 2 weeks ago, if I remember correctly, by Julian here in the Zoominar. But roughly speaking, it's the integral over the boundary of K of a time average rotation number, which measures the degree to which a distinct Reb trajectory twists counterclockwise around each other. So it's basically you at every point you average the rotation number, and then you take the integral of this average rotation number over all K, over the entire boundary of the convex domain. And then, using this criterion, they build, using the construction from Abondandolo, Bramam, Hryniewicz, and Salomao, they build in a very similar fashion. So they construct a 4-dimensional convex domain, which is not symplectomorphic to a convex domain. So construction of a 4-dimensional convex domain, sorry, dynamically convex domain, not symplectomorphic to a convex domain. So that was kind of a relief, but we still don't know for the construction of Abondandolo, Bramam, Hryniewicz, and Salomao if it is symplectomorphic to convex or not. This criterion, I mean, does not apply to, I mean, this criterion does not conclude for this C epsilon. So third idea for being symplectically convex was to say, well, maybe if we add condition to being dynamically convex. So let's say being symplectomorphic, being symplectically convex would be being dynamically convex and being toric. That might seem a bit unnatural. So let me explain where does this idea come from first. So let me first recall what does mean being a toric domain. So definition, a toric domain x omega in Cn or R2n is a set of the form x omega is the preimage by the moment map of a domain in the first orthant. So this preimage where omega is a domain in the first orthant of Rn. And mu is the moment map, or the periodic moment map from Cn to the first orthant, sending Z1, Zn to pi module of Z1 squared up to pi module of Zn squared. Yeah, so a few examples is if I take the preimage of this triangle of size AB, so it's the ellipsoid EAB. right? It's the set of Z1, Z2 in C2 such that pi module of Z1 squared over A plus pi module of Z2 squared over B is less or equal than 1. That's the complex ellipsoid of axis AB. I really like toric domain because they allow me to draw in the plane 4-dimensional manifold while retaining a lot of information. So let me do 3 more examples, which I will need later on. One is the preimage of a rectangle of size AB, that is the polydisk AB. So it's the product of a disk of area A and a disk of area B. And other examples are, I can draw a cylinder. So that is the preimage of this infinite strip of size A, that is the cylinder of size A. And I can also have this non-disjoint union of cylinder, and that's going to be the preimage of this L-shaped strip. Now that I will call this NAB. And it's called, I'm going to say it's a non-disjoint union of cylinder of size A and B. Then a toric domain is called monotone. So a toric domain X omega is monotone if let me draw a picture and then write a proper definition. If at every point of this boundary, the normal vector at that point has all components which are non-negative. So if for all x on this positive boundary, so in, let me call it d plus omega, so that would be the boundary of omega intersect with the interior of the first orthont. For all x, the normal vector to omega at x has all components non-negative. So this definition, which might appear slightly out of nowhere, it's actually, we introduced it with Michael Hutchings and Vinicius Ramos. So Hutchings, myself, Hutchings, and Vinny. Is a toric domain in R4 is, so a toric domain is dynamically convex if and only if it is monotone. So it's a nice geometric description of being dynamically convex. So a toric domain X omega in R4 is dynamically convex if and only if X omega is, well, actually strictly monotone. But let's skip on that detail for a second. And then we proved, again, with Hutchings and Vinicius Ramos, that on monotone torics in R4, all ball normalized capacity coincide. So the statement of the strong Viterbo conjecture is true. So the Viterbo conjecture is true. So the weak Viterbo conjecture is true. So we avoid this problem or this result of abundant hologram Mriniewicz and Salomar. So all ball normalized capacities coincide on monotone toric domain in R4. And maybe let me emphasize that those lemma and theorem are really restricted to the 4-dimensional case. It doesn't, they do not extend really. Like it is true that monotone toric domain are dynamically convex, but it is not true that toric dynamically convex in R6 are necessarily monotone. So this is really a 4-dimensional lemma. And then we say, okay, let's go back to convexity. Now we know why we say dynamically convex and being toric, so it's being basically monotone toric. How good is that for replacing convex? The expectation is that it's a smaller subset of the set of convex domain, but then again, no. And that's lemma, which was due to Hutchings, and then we generalized it with my PhD student J.Dardennes and J.Zhang. Is if you take any toric domain, x omega, which intersect the axes at A and B, then the real invariant of x omega, we can actually compute it, and it is equal to A plus B. Why am I saying this? Let me go back, because I'm going to apply the criterion of J.Dardennes and M.Pereira that we are symplectomorphic to a convex domain implies that the product systole times this real invariant divided by the volume is bounded above and below by constant. And maybe one more remark is their construction, they break like this inequality. They can make this this ratio goes to 0. And I mean, once we have this lemma, it was pretty clear what picture to draw, and then theorem by J.Dardennes, myself, and J.Zhang is that any actually monotone toric domain can be deformed to a monotone toric domain, which is not symplectomorphic to a convex domain. So any monotone toric domain can be, I want to say deformed and not perturbed, but can be deformed, let's say, through monotone toric domain to a monotone toric domain not symplectomorphic, which is not symplectomorphic to a convex domain. And the idea is really take a monotone toric domain And then you're just gonna add like a very long spike, very thin and long spike along the axis. So you're just gonna increase the Ruel ratio as much as you want. And making the width of the slide very small, you essentially do not change the volume and you do not change the systole. So you make this ratio goes to plus infinity as if you pull sufficiently, if you strain it for sufficiently large. And actually this deformation is small with respect to symplectic capacity. So moreover, this deformation is small with respect to symplectic capacities. In other words, symplectic capacity is what I want to say is the symplectic capacity of the deformed domain are epsilon close to the symplectic capacity of the original domain. So capacity are not the best tool to detect convexity. Okay, so those were a few ideas. Then there was a fourth idea for what is symplectic convexity. And the fourth idea was, well, we don't really know dynamical convexity. Adding toric doesn't work out perfectly. We are interested in the strong Viterbo conjecture, so suggestion. Actually, let's define something called Viterbo convex and just say symplectic convexity is domains on which all normalized capacity coincide. So say symplectically convex is where, I should call it Viterbo convex, where all normalized capacities coincide. And then I put normalized and I didn't put ball normalized as before, because this ball normalization is not very natural. It comes from Gromov theorem. It's like a historical reason, not an intrinsic symplectic reason. And one could think about putting different normalization. So for instance, if you define the cube, let me call it delta and delta. So this is the polydisk whose all disk have size delta. Then you can define the cube capacity. That's the definition due to myself and Hutchings. You define the cube capacity of a symplectic manifold to be the largest cube, the size of the largest cube you can symplectically embed in X. So the cube capacity C cube of a symplectic manifold X omega. This is the supremum of delta such that there exists an embedding from the cube to X. And with Michael, we proved that if we look at the cube and this non-disjoint union of cylinder, so the largest cube you can put in the non-disjoint union of cylinder, each of the cylinder having the same size, is the one you can include. So you also have a non-squeezing. Like on the picture, it would be, so you have this L strip where those two sides are the same. And then you can include a cube here. And actually, this is the largest cube you can symplectically embed in this non-disjoint union of cylinder. And then, well, when we have this, so definition, that is due to myself, Miguel Pereira, and V.Ramos, is we're going to say, well, a capacity is cube normalized if it is one on the cube and one on the non-disjoint union of cylinder. So a capacity C is cube normalized if C of the cube of size 1 is equal to the capacity of the non-disjoint union of cylinder all of size 1 is equal to 1. Examples of cube normalized capacity. Well, first example is this cube capacity is of course cube normalized. But it is not ball normalized. Yeah, for instance, the cube capacity of the ball of size 1 is 1/2, whereas the cube capacity of the cylinder of size 1 is 1. A second example is due to Chelebach and Monke, is called the Lagrangian capacity. So let L in the symplectic manifold X omega be a Lagrangian submanifold. Then we define the minimal area of L to be the infimum of the omega sigma, such that sigma is an element of pi2. I mean, sigma is going to be a disk whose boundary is on the Lagrangian, and you take the area of the symplectic area of the disk. So it's omega sigma. Sigma is in pi2 of X relative to L, and omega sigma has to be positive. And then the Lagrangian capacity is defined as CL of X is the supremum over all those areas such that L is an embedded Lagrangian torus. Note that this is also one of the first capacity which is not directly related to the dynamics on the boundary. And then I think that was the main result, I mean, stated differently, but rephrased in our context, main result of Miguel Pereira's PhD is that this Lagrangian capacity is actually cube normalized. I mean, his PhD prompted this project that I'm going to talk about. Then with Miguel and Vinny, we proved that for cube normalized capacity, they all coincide on monotone toric domains. So all cube normalized symplectic capacity coincide on all monotone toric domains in R2N. So this is true. This is true in every dimension. So we have like an equivalent of a strong Viterbo conjecture for cube normalized capacity in any dimension for all monotone toric domains. So of course, conjecture, cube normalized capacity coincide on all convex sets. So cube normalized capacities coincide on convex sets in R2. But now, let me go back still to this convexity. We say, okay, new definition, Viterbo convex is where all normalized capacity coincide. But then if we have this strong Viterbo conjecture in mind, we can look at ball normalized capacity or cube normalized capacity. And the first question was, oh, but is the set of domain on which ball normalized and cube normalized capacity coincide the same? And the answer is no. So it's not a good definition. And so let me call it a counterexample. Let me change pace so I can do a nicer picture. I'm gonna take the toric domain, which is gonna be the preimage a domain like this. So we start, let's say this is 1. Start with the ball. Then, so I'm gonna call it XA, which is gonna be the preimage of this domain. So this 1 minus A, this is 1 minus 2A, this is 1 minus A, 1 minus 2A. I take this domain here. So non-monotone, absolutely non-convex. Yeah, and so A is a real number between 0 and 1/2. When it's 0, it's the ball. When it's 1/2, it's basically completely touchable. And for here, I mean, it's various results with both Michael Hutchings and then with M.Pereira and V.Ramos. We could compute essentially everything. By that, I mean, we could compute that the Gromov width of XA is the minimum between 1 minus A and 2 minus 4A. The cylindrical capacity of XA is equal to 1 minus A. The cube capacity of XA is the minimum between 1 minus 2A and 1/2. And the Lagrangian capacity of XA, which is going to be equal to the, I haven't defined, but the smallest non-disjoint union of cylinder in which you can embed XA is equal to 1/2. Conclusion of this, of all those computation, is cube normalized capacity coincide if and only if A is between 0 and 1/4. That's cube normalized capacities coincide. Whereas ball normalized capacity coincide for any A between 0 and 1/3 and do not coincide if A is larger than 1/3. So here there's a discrepancy for A between 1/4 and 1/3. And if you're interested in like the standard Viterbo conjecture, well, the standard Viterbo conjecture is true for all A between 0 and 2/5. So if and only if any ball normalized symplectic capacity of XA squared is less or equal than 2 times the volume of XA. So again, saying symplectically convex is where all normalized capacity coincide is not actually well defined. So then I should put ID5, but that's another story. I'm gonna stop here. And thank you very much.
Thank you very much for the beautiful talk. Are there any questions?
Maybe I have a question concerning this perturbation theorem, right? That you can perturb monotone toric domain to a non-convex. So how large is this perturbation in this Banach-Mazur distance?
Very small.
It's very small.
It's extremely small for the Banach-Mazur distance, the fine where you ask things to be composition to be unknotted.
Yes.
Because actually this really thin, you fold it. You can fold it along the boundary, and folding is basically isotopic to I mean, it's essentially an isotopy. So it's, and then you embed it into like an epsilon neighborhood.
So convexity is not a robust property with respect.
Nope. It doesn't look so, at least.
I see. Okay, thank you.
I have a question. So this example that you gave for where the cube capacities don't coincide is, I think, non-dynamically convex, right?
No, it's non-dynamically convex. Yeah, of course.
So my question is, do you have an example for a dynamically convex, but like non-toric domain for which not all of the cube capacities coincide?
No, is the short answer.
Okay.
Because,
like, do you think it could be that they coincide for all dynamically convex domains, or?
I mean, my impression is that cube normalized are going to be slightly finer than ball normalized to detect embedding. So I would guess that on the example of Abondandolo, Brahma, Mrinievich, and Salomao, cube normalized also are not the same, but
okay.
But it's a guess. It's actually, they are very hard to compute.
Okay,
in general.
I also have another question. So you said that in dimension 4, so when the kind of toric image is 2-dimensional, then being monotone and dynamically convex is the same, and then it's in higher dimensions.
For toric, yeah.
For toric, yes. Only in the kind of toric regime, but in higher dimensions, this is kind of not true. So my question is basically, do you think there exists like a kind of a weaker definition of monotonicity that will be equivalent? Because like you're demanding basically all of the coefficients, or like the entries of the normal to be positive. Like maybe you should demand, I don't know, they're like the average of these is positive, or, you know, pointwise.
I hope so. I try regularly. I still haven't had a good condition which will ensure dynamical convexity.
Okay.
So no, still under progress. I don't have it. I hope there is one.
Any other questions?
I have a question. Can you hear me?
I'm hearing you.
Oh, great. Okay, cool. Sorry. Yeah. So can you just say one more, before I say my question, can you just say what the cube normalization condition is again? Just one more time.
Sure. So it's on the cube. So the polydisk of whose all disk have size 1, you ask the capacity to be 1. And on this non-disjunct union of cylinder, all of which have like sectional area 1, it's also equal to 1.
I see. So, I mean, I guess like, is it like, I don't know. It seems like, I guess my question was sort of like, is it possible to see both of these normalization conditions as sort of living in some single class of normalization conditions that sort of you would expect to be true for convex things? You know what I mean? Like that's like
I know exactly what you mean. We try to pursue in that direction, but got nowhere so far. But yes, we guess you could find like a bunch of normalization condition all coming from some squeezing. At some point we tried saying, oh, maybe it's like a ball and this non-disjunct union, can we try like for LP norm balls and things, but we never reach like non-squeezing for those or enough to find a nice domain. But it would be very interesting to see it, yes, as a family of conditions. Also, there are inequalities between like cube normalized and ball normalized capacities with this factor of n.
You're saying that they're related, the two, like if they're, yeah, okay, that makes sense. Yeah, because I guess maybe the thing you're doing is you're saying like I take some symplectic manifold or some subset of R2n and then another subset of R2n, and I take kind of the place where they're critical. Like I take the like maximum embedding of one into the other, and then I say the capacities of those two things have to agree, and that's what I mean by normalized with respect to that pair.
Yes.
And then you could say, and then you just want to know which of those normalization conditions is sort of characterizing things that maybe would be true for all convex things or something, and why. Yeah, it's a really interesting question. So you feel like you didn't make any meaningful progress on that?
Yes, so far no. But
okay.
Yeah, it's not
Any other questions? Well, if not, then let's thank our speaker again.